Here we are, we've got 706 part 3, the last video on conservation of energy, and we have another AP problem here. So we have a person, I'm going to go ahead and read it again. I know the quality isn't great on this print. A person starting from rest at point 1 swings along a circular arc from a rope as shown above. Point 2 is at a lower height than point 1. What is the trajectory of the person when the person lets go of the rope at point 2? So they're starting here, they're swinging to here, here's where they let go, and we want to know which one of these best represents their motion. Well, right away we can eliminate C and D because we know that when an object is released from circular motion, it travels tangentially to the circle in a straight line, and we don't have that here, and we don't have that here. So we know that it has to be A or B. So we look at A, the person would rise up to the point of release. And if we look at B, the person would rise up to a point slightly beneath the point of release. So what we would have here is perfect conservation of energy. What we would have here is a little bit of loss of energy. So I should have had you guys pause this and see if you could solve it on your own. Sorry, I just thought about that, but we're just going to keep going. So in reality, what we're going to see is that the height is going to be here because it's hardly ever perfectly conserved because we always have things like friction. We always have things of loss to mechanical energy to sound. So the answer here is going to be B. So on the next one, I'll make a point of saying pause it and see if you can answer it. Okay, moving on, next question. All right, we have a scenario. This is the initial, and then this is the final. And you'll notice there's a lot of diagrams with AP problems. They do this so that there is not confusion on what they're trying to talk about. And since this is blurry, if you don't have the problem at home, I will read it. A block of mass M is launched by a spring of negligible mass along a horizontal surface of negligible friction. The spring constant of the spring is K. The spring is initially compressed a distance of x sub O. The block is released from rest. Sometime after the block is released and travels in the direction shown in the figure, the spring compression is x sub F. Which of the following mathematical calculations can a student use to determine the speed v sub F of the block at this new position? So A says 1/2 kx squared equals 1/2 mv squared, solve for v sub F. B says 1/2 kx squared equals 1/2 kx squared plus 1/2 mv sub F squared. C is force perpendicular times distance equals 1/2 mv squared, and force perpendicular equals kx, solve for V. Force times distance cosine theta equals 1/2 mv squared, and F equals kx, solve for delta V. All right, so if you want to try to work on this on your own, pause the video, and then when we come back, we'll see how you did. All right, so when I look at this problem, I think right away, well, conservation of energy is probably going to be the easiest way to solve this. So while these seem plausible, these two both use conservation of energy. So this is over here, I have spring energy. I have elastic equals kinetic. And down here, I have elastic equals kinetic plus spring, actually vice versa. So, and I'm just going to toss these out. These do not seem like the best choice because we're working now with two equations, and we can usually with conservation of energy do what we need to do with one equation. So the question is, which of these two is correct? And your initial guess might have been this one, but if that was the case, you didn't look at the diagram closely enough. So when the spring is unstretched, it's going to reach this point. So this was a key to solving this problem. Because the spring is still partly compressed, we haven't released all of the spring energy yet. And so to answer this problem, we do have our initial spring energy, our elastic potential energy. But because at this point, the spring is not fully uncoiled, we have kinetic energy and elastic potential energy. And the answer there is going to be letter B. All right, that wraps up conservation of energy. And so let's look, I'm just going to kind of throw power in here. And we're going to just talk briefly about what power is. So power, by definition, is work per unit of time. So we say that power, which is capital P, is work divided by time. So the unit here is the watt. That is the metric unit. And if we wanted to, we could find out that if we took a kilogram meter squared per second squared and we divide that by time, that's going to flip. So that would be a kilogram meter squared over second. And our let's just look at a sample problem. A 193 kilogram curtain needs to be raised 7.5 meters at constant speed and as close to 5 seconds as possible. The power ratings for 3 motors are listed at 1 kilowatt, 3.5 kilowatts, and 5.5 kilowatts. Which one is the best for the job? I need to find my pre-calcs. There we go. So if we have power is work over time, I can expand this to be force parallel times distance over time. It gives us a distance. We have x is 7.5 meters. We have a mass of 193 kilograms. And one of the keys here that we needed to see was constant speed. So here's the implication for that. If I draw a free body diagram, we're moving at constant speed. We're going to have, let's see what's raising it, probably tension. And our weight vector are going to be equal and opposite. And so I know that the this one, if we do a standard coordinate system, if we make up positive, this will be negative and this will be positive. So if this is negative mg, this is going to be positive mg. So what I can say here is that my power is going to be equal to mass times gravity times distance over time. And we want to raise this in 5 seconds if we can. So I'm going to take 193 kilograms times 9.81 times 7.5 meters, divide that by 5 seconds. And when I do, I get 2,839 watts. If I put that into kilowatts, it's going to be 2.8 kilowatts. So which one of these motors work best? Well, this one's not going to have enough. This one's going to have way more than we need. This one's going to be pretty close. It's going to have enough power to get the job done. Why not just buy the 5.5? Well, maybe if you have other jobs you think you need a 5.5 for, okay, but remember, you pay for power. And so you're going to have a much higher price tag on that motor versus this motor. So save yourself some money. Okay, so that was just very quickly power, and that wraps up our chapter on work and energy and conservation of energy. So thanks for watching. Next time, in the next chapter, we're going to go on to momentum. That's all for now.